my name is Einab, and here is Gal. We will talk about our homework. So regarding question 1, we go over it quickly. We defined the segments of the audio of the WAV file, and we did it using the spectrogram. We generated the spectrogram, and we took from there the timing and the amplitude, and the frequencies are a bit hard to tell from spectrogram. So we also computed the exact frequencies using FP. The top 10 frequencies, and that's it. So we took the segments, each one we generate sine wave for it, and then we reconstructed the file. It sounded really good. The only comparison that we saw from the original file was the amplitudes, because we gave the sine waves only amplitudes between 0.5 and 2.5, and those amplitudes weren't matching the exact amplitudes of the original file. So here where we saw the difference. So here you can see the difference in the amplitude and in the spectrogram. The difference is exactly in the brightness of in the colors of the amplitude. Okay, so we'll skip question 2 and 3 because it's the same question, and we'll go to question 4. Okay.
Okay, so in question 4, we were asked to downsample or to resample our original waveform in order to have only 4 frequencies. We recall from the lecture that we learned our theorem that tells us that this frequency we need twice the sample rate. So what we did is plotting the frequency domain across all the waveform, and we could observe that up until 2000 hertz, we have 4 frequencies which are quite significant by their magnitude. So we thought that we suggested downsampling to twice this frequency, namely 4000 hertz. And indeed, we could verify that there are 3 to 4 significant frequencies until 2000 hertz. So what we did is downsampling our waveform to this new sample rate. And what we get is the elimination of the high frequencies, but not exactly eliminating it. It's just because the sample rate is too low, then the higher frequency just squashed all over the lower ones, and upsampling again to the original sample rate cannot help us recover from this loss of information. So we end up with around 2000 hertz as the highest frequency in the upsampled waveform. In question 5, we compare some methods of reconstructing a waveform out of a spectrogram. So first, what we do is following the note in the question, we crop the original waveform number of samples to match the reconstruction waveform. First, we do one round trip of short-time Fourier transform and back inverse STFT. And what we get is very similar or completely similar waveform to the original one. The differences cannot be perceived, at least for us. Then examining the Griffith and Lim algorithm just after its random phase, namely the very first iteration, we can see that the waveform is very different in its structure from the original one. Mainly because we know that we cannot assume that the phase of the signals composing the original signal is correct, and this is only random phase. And we can see that not knowing the phases can be very can affect heavily the reconstruct waveform. And indeed, doing full amount of iterations of Griffith and Lim provides a better reconstructed waveform, much better. It sounds very similar to the original one.
Let's jump to
for the last comparison. So doing the comparison in question 6 between the perfect reconstruction resulting one round trip of STFT to inverse STFT. Indeed, it sounds very similar. We cannot really differentiate it between the two. However, we know that the Griffith and Lim algorithm does not guarantee the exact same waveform, since it converges into a local optimum and not necessarily the original one.
In the phases. Yeah.
Yes, and the phases does not converge into completely the original one, and I think that's it.
Okay. Thank you.
Thanks.